Right, so welcome to 3.5. We're going to take those large numbers we talked about in 3.4 and make them into something called scientific notation. All right, so evaluate these expressions. That's 10 squared, which is 10 times 10, 100. That's 10 cubed, 10 times 10 times 10, 1,000. So what's 7 times 100? 700, right? Now, what's 7 times 10 squared? Well, we just said 10 squared and 100 are the same thing, so this also must be 700. Now, 8.2 times 1,000. Now, you could sit there and multiply, but we learned a shortcut, right? Times 10 times 100 times 1,000. So there's two empty spaces there. We're going to fill them with zeros. It's 8,200. And so, same, if this is times 1,000, 10 cubed is also 1,000, so we also move this 3 spaces, put 2 zeros in, and it has the exact same answer. If you did numbers 4 and 6 there, you can already do tonight's homework. Because what these weird things, 7 times 10 squared and 8.2 times 10 cubed, or 10 to the third power, they're called scientific notation, and they're a way to write very large numbers. Now, 700 is not a large number by scientific notation standards. There's a large number. What number is this here? Okay, well, let's remember. These are thousands, millions, billions. What's next? Trillions. That's quadrillions. That's 582 quadrillion. Now, if you had to do this multiplication that you see there, which is 9,700,000,000 times 60 million, if you try and do that on your calculator, one of two things is going to happen, right? First of all, if you actually had to do it on paper, realize you would have rows and rows and rows of zeros that you'd have to deal with, and you would never want to do that. Even on a calculator, if you try to do it on many calculators, you're going to get an error message. And the reason you're going to get an error message, it doesn't have room for all those zeros. Now, good calculators, though, have a way to deal with this. And what they would do, instead of running out of room and putting error, for this number, they would write 5.82 times 10 to the 3, 6, 9, 12, 15, 17th, I believe. And they would write that number that way. And it's called scientific notation. And I will tell you, there are not 17 zeros there, by the way, but we will show you how that is done. All right, so scientific notation, not difficult, but does have a lot of rules, okay? So I want you to look at these two numbers and tell me which one is correctly written in scientific notation. Well, it says there's two rules. The number is always multiplied by a power of 10, right? That's why we learned about powers of 10. So both of them satisfy that. But then the second rule says the decimal point is always after the first digit. Well, that one has the decimal point after the first digit, right? You read numbers left to right. So 4 is the first digit, and the decimal point is right after it. 41 has a decimal point. It's after the second digit there, and so that is not scientific notation, okay? All our answers will have a number, then the decimal point. So which one of these is in scientific notation? They're both powers of 10, but again, this is before the first digit, not after it, not allowed. So it has to be after the first digit. Now, one of those has the decimal point after the first digit. Which one? Well, this one, right? You know, you might be tempted to write 6.0 times 10 to the 8th, but we don't do that, right? When we have 6.0, we just write 6. And so the decimal point there is after the first digit. That's allowed. This is no good. That's not scientific notation. You could multiply those two numbers. Oh, and by the way, that x is for times. Hopefully we all realize that. It is not the variable. And which one of these? Again, it's 9 times 10 to the 4th. Now here, that's a power of 9. So there were two reasons, plus the decimal point is after the second digit. So there's two reasons that one's wrong. All right, so your answers have to look like that. Now, how do you do the work, right, is the next screen. Okay, so first of all, be able to say that number. That's 145,000. So the whole point of this is to be able to not write those zeros. So we're going to write the non-zero numbers, and we're going to move the decimal point behind the first digit. So we're going to write 1.45. It's always times 10. Now what we have to do is figure out the exponent here. And it equals the number of moves of the decimal point. So let's see that. 145,000 had a decimal point right there. And then we moved it 1, 2, 3, 4, 5 times. And so it's 1.45 times 10 to the fifth. Notice it's not how many zeros, it's not that, it's how many moves. Let's try this one. So we're going to get rid of all those and write 3 times 10. Now 10 to the what? 1, 2, 3, 4, 5, 6, 7. So this is 3, that's 30 million, by the way. That's 3 times 10 to the 7th. So here the zeros match, but here they don't. And so please, how many zeros there are is not the rule. It's how many moves of the decimal point. Now the comma helps you because the comma is every 3, right? So there's 3, 6, and then one more to get behind the 3, right? It's not in front of the 3, it's behind that first digit. All right, so now you can get rid of the zeros on the end. That zero in the middle is called a trap zero, so that has to stay there. The decimal has to go behind the first digit, so it's 2.07 times 10 to the what? 1, 2, 3, 4. 2.07 times 10 to the fourth is this number, 20,700. So that's what you're doing. All right, so typically in a word problem or a science class is where you'd see this. So the real distance around the equator is 40 million meters. Okay, a meter is a little bit more than a yard. So you know what a yardstick looks like. Think about 40 million of those. Now, so we get rid of all the zeros, and it'd be 4 times 10, and there's 1, 2, 3, 4, 5, 6, and there's the 7th one. And since it's a word problem, we're going to write m for meters, or just write the word. And the distance around the Earth is 4.10 times 10 to the 7th meters. All right, so now we're going to go backwards. It's not tricky. It's just move the decimal point back. How many times do we move the decimal point back? 4 times. So right, we're going to make a big number. 1, 2, 3, 4. Now, we moved it 4 times. How many empty spaces did we make? We made 3. And then we're going to put our comma in the correct spot because big numbers need commas, right? They go every third. So 1, 2, 3, and what number is that? That's 63,000. Next. So take it, go 1, 2, 3, 4, 5, 6. Add those zeros, and then let's put some commas in it and make it neater. So it's this. Let's be able to say that out loud. That's 7,170,000. All right, so where is the decimal point right now at the start? Is it at A or is it at B? It's at B. And then you move it 5 times. 1, 2, 3, 4, 5. We have 5 empty spaces this time. And we put the comma right there, and that's the number 200,000. All right, so now we're going to see which one of those is larger. Now you could sit there and change them to regular numbers. Absolutely could do it that way, but there's a shortcut. The bigger, when they're in scientific notation, the bigger number has the bigger exponent. So which one's bigger? 6 is bigger than 4. That's the bigger number, the larger number. Now let's just double check that since we're just doing the first one. 1, 2, 3, 4. That's 23,000. Now this one, you move it 6 times, you're going to get 5 zeros, right? 1, 2, 3, 4, 5. That's 2,300,000, right? These numbers are not close, right? Because every time you make that one bigger, it's times 10 bigger. So this was times 100. This times 100 makes that one, right? You would move the decimal twice more to make that one. It's 100 times bigger, just because this is 2 bigger than that. Try this one. So, right, you could trap people because you think 9.9 is bigger than 4.4, but no way. 6 is way bigger than 2. It's that one, right? You move this twice. That's only 990. Move this 6 times, you're going to get 5 zeros. That's 4,400,000, right? You don't even need to look at these numbers unless you have a tie with the exponents. If you have a tie with the exponents, then you look at that first number. All right, we're at practice. Do these 4. Be able to go back and forth. So this is 3 times 10, and we're going to 1, 2, 3, 4, 5, 6. This is 2.84. It can't, anytime in this you see 28.4 or 284 or 0.284, it can't be right. Has to start with 2.84, decimal behind that first digit. And this time we have 1, 2, 3, 4, 5, 6, 7, right? It's not the number of zeros. To make it back into standard or decimal form, it's called, we're going to go 1, 2, 3, 4, 5. We're going to have 4 zeros. That's 370,000. This one, we're going to have 7 zeros. I make 7 spaces, right? Because we move it at 7 times. 4, 5, 6, 7. And we're going to put our commas. Notice it's hard to say the number without the commas. What number is that? That's 50 million. So the mass of an asteroid, so mass is the weight of something in space where there's no gravity, right? So the mass there is that, which is what? 406 billion. 406 billion is 4.06, because you can't get rid of that trap zero. It's in between two other numbers. You can only get rid of the ones in the end. Okay, so we're going to go 3, 6, 9, and then 2 more, times 10 to the 11th. And this is kgs, kilograms. And which one's the largest? You don't even have to look at anything other than that. Good luck on the homework.